Austin, am I audible? Austin, am I audible? Austin, are you there?
Yes, sir. Yes.
Okay. So in the previous class, we discussed about the elevation in boiling point as well as relative lowering in vapor pressure, right? Do you have any doubt from the previous class?
No, sir.
Okay. So let's just start the next colligative property, and that is your depression in freezing point. Depression in freezing point. So see what happens when you are going to add a non-volatile solute in a volatile solvent. The vapor pressure decreases, and hence the depression, basically the freezing point will also decrease. So first of all, I'm going to introduce this, define this freezing point. What is this freezing point? So freezing point is the temperature freezing point is the temperature at which the vapor pressure, Vp stand for vapor pressure of liquid state becomes equal to the vapor pressure of solid state. So basically, the temperature at which vapor pressure of liquid state will be equal to the vapor pressure of solid state, that temperature will be your freezing point. So whenever you are going to add a non-volatile solute in a volatile solvent, it will the depression there will be depression in freezing point. That means let's say initially if the water is a volatile solvent, it freezes as at 0 degree centigrade. Then after adding non-volatile solute, the freezing point of solution after adding the non-volatile solute, it will decrease, and that is called depression in freezing point. Now I'm gonna draw a graph as we did in case of elevation in boiling point. So the graph will look like this. Let's see, I'm gonna show you. So the graph is basically vapor pressure versus temperature. The another graph I'm going to show you like this. This is for solution, and this is your for frozen solvent. Frozen solvent. And this one that I'm going to show you, this is your liquid solvent. Liquid solvent. And this is the black one is for solution. So basically, you can see frozen solvent. You can see that this temperature, at this temperature, let's say at this temperature, This is the freezing point of the pure solvent. T naught F, when it is pure, the solvent is pure. And this is the point, or this is the temperature at which the solution freezes, at which the solution freezes. What does it mean? You can see when the solvent was pure, the freezing point is this, and when a non-volatile solute added, the freezing point is this. That shows that that actually shows that when you are going to add a non-volatile solute, there will be depression or there will be decrement in freezing point of the solution, and this difference is known as delta TF. Delta TF, as we did in elevation in boiling point, delta TB. Now, again, the same thing will be repeated. Delta TF will be equal to, here in the elevation in boiling point was that was equal to the boiling point of the solution minus boiling point of pure solvent. But in freezing point, we take freezing point of pure solvent minus freezing point of solution. Freezing point of solution. So here I'm going to write T naught F is the freezing point of pure solvent. Freezing point of pure solvent, and TF is your freezing point of solution. Please do write up to this and then let me know. And then I'll move ahead and derive a formula.
Yes.
Very good. Now see, again in the same way, experimentally, we found that this delta TF directly proportional to molality. And to remove this proportionality sign, we are going to use a constant, that is Kf. And Kf is your molar depression constant. This Kf is constant, that is known as, also its name is cryoscopic constant, and we can call it molar depression constant. Molar depression constant. And again, you can calculate the unit of this Kf, and it will be similar or same as the elevation in boiling point. You can see this is your change in freezing point. So it will be in Kelvin. And what is the unit of molality? That is mole per kg. So the unit will be Kelvin kg per mole. Kelvin kg per mole. This is the unit. So please do write it. Now I'm going to give you a question. Very good. what amount of ethanol C2H5OH that is your ethanol assumed to be non-volatile must be dissolved in 1 kg of water so that it freezes at -2 degrees centigrade. -2 degrees centigrade. Freezing point of water is 0 degrees centigrade, that is pure solvent, and K cryoscopic constant for H2O. And also remember that this constant K for Kb depends upon the nature of solvent. It is given that it is 1.86 Kelvin kg per mole. Please do write. Austin, will you be able to solve it?
Yes.
Okay, please do it. Oh, very good. So the mass that you have calculated will be 49.4 grams. Very good. Now I'm going to give you another question. Please do this. Oh, wait. Please do this. Molality of the just wait a minute. See, it's as I told you, this K depends. Please do write it also in a note on nature of solvent. Nature of solvent. So it will remain unchanged. It will remain unchanged. It is constant. So whether you are going to increase the molality or decrease the molality, it will unchanged. So the answer will be C. Constant it will be. Is that clear?
Yes.
This question is based upon Raoult's law. Just wanted to test you that whether you forgot it or still remember. I'll give you one more question. Yes, no problem. See, it's very easy. You just need to obtain information what is given in the question. So first of all, as you can see, vapor pressure of two liquid P and Q are 80 and 60 torr respectively. Okay. So basically that means P naught P. This is the pure vapor pressure of P, that is 80, and P naught Q, that is pure vapor pressure of Q, is 60. The total vapor pressure of solution obtained by mixing, we need to calculate PT. We need to calculate PT. Okay, and it is given that number of moles of P is 3, and number of moles of Q 2 moles of Q, 2 moles. These are moles. Now, as you know that total pressure of the solution will be equal to partial pressure of each component, partial pressure of P plus partial pressure of Q. Now, what I'm going to do, I'm going to calculate the partial pressure of P, which is equal to P naught, pure pressure of P into mole fraction of P. So, in order to calculate the mole fraction of P, that will be equal to number of moles of P upon total number of moles. That means number of moles of P plus number of moles of Q. So number of moles of P is 3 upon 3 plus 2, that is equal to 3 by 5. And we also need to calculate the mole fraction of Q. That will be number of moles of Q upon total numbers, that means 2 plus 3, that will be equal to 2 by 5. Now, you are going to just substitute the value. What is the pure pressure of P? That is 80, and you can see the mole fraction of P is 3 by 5, and you can easily cancel this 16 times, and here the partial pressure of P will be equal to 48 torr. Since it is given in torr, so I'm going to write it in torr. Now, torr is the unit of pressure. Now, partial pressure of Q, that will be equal to pure pressure of Q into mole fraction of Q. Now, pure pressure of Q is also given, that is 60, and we just calculated the mole fraction of Q, that will be equal to 2 by 5. So you can easily cancel this as well. And you can see here it will be 24 torr. Now, what you need to do, just add the partial pressure of P and Q. Here it will be 48 plus 24. That will be equal to the total pressure of the solution, that will be equal to 72 torr. Is that clear? So the answer will be A.
Yes.
Please do write it. Humamuddin, did you just join? Humam, please do respond. And
Sorry, sir, I'm actually traveling. That's why.
okay, no problem. Are you able
Sorry.
to? Am I audible clearly to you?
Yes, sir.
Okay, I will just slide it up and I'll show you whatever I taught right now. That is depression in freezing point. You need. I'll just explain and take a screenshot. Austin, are you done with this?
Yes, sir.
Okay, Humam. So this question that I just gave is on Rawls law that you have already studied, right? And we just started from here. Humam, depression in freezing point. As we discussed about the elevation in boiling point in the last class, this is your depression in freezing point. When you are going to add non-volatile solute, then the freezing point of the solution will decrease. And you can see elevation in boiling point, what happened there. When you are going to add non-volatile solute, the boiling point of the solution will increase as compared to the boiling point of the pure solvent. So what is freezing point? Freezing point is that temperature at which the vapor pressure of liquid becomes equal to the vapor pressure of solid state. Okay, in solid state. So both the vapor pressure of physical state, solid and liquid, becomes equal. That temperature is your freezing point. Now we plotted a graph between vapor pressure and temperature, and here is the graph. This is the graph for liquid solvent, that means pure solvent. And here you can see it started frozen. It started freezing. That means this is the temperature at which it start freezes. That means this T naught F is the freezing point of the pure solvent. But when you are going to mix non-volatile solute, the freezing point of the solution decreases and the freezing of point of solution is here, that is TF. Now again, the difference between these two freezing point is known as delta TF. Delta TF is equal to T naught F minus TF. Always remember that in elevation of wait a minute, in elevation in boiling point, delta TB was equal to TB minus T naught B, but here in delta TF it is equal to T naught F minus TF. Basically the bigger or the larger value will be first and the smaller value will be at last. So T naught F here is your freezing point of pure solvent and TF is freezing point of solution. Please take a screenshot.
Taken, sir.
Very good. Now, again, in the same way, we found that delta TF is directly proportional to molality. And to remove this proportionality sign, we are going to use a constant that is Kf. And Kf is known as cryoscopic constant, or we call it molar depression constant. Molar depression constant or cryoscopic constant. And always remember that this constant, whether it is cryoscopic constant or ebullioscopic constant, that was in elevation in boiling point, that depends upon depends upon the nature of solvent, not on solute. Okay, this constant depends upon nature of solvent. And we also did the unit of kb, that was Kelvin kg per mole, and here the unit of kf is Kelvin, again the same Kelvin kg per mole. Is that clear?
Yes, sir.
Okay, now take a screenshot of this question and we will discuss it. Now you are going to try it at home, and if you want or don't get the answer, let me know in the next class. Done?
Yes, sir.
Okay, the next question I'm going to just explain. There is a question that is, if molality of dilute solution is doubled, the value of molar depression constant, that is Kf, will be. So as I told you, this Kf depends only on the nature of solvent. So it will not change, and the answer will be, it will be unchanged. Okay. If you will change the solvent, it will then change. Can I change the slide?
Yes, sir.
Okay. Now I'm going to give you a question on this, and then we will move to the next colligative property. And the question is this. I'm going to give you option as well. Just wait a minute. You can read the question and start solving it. The option is this. The question is very easy. This is not what is given and what you need to calculate. Very good. Okay, Humamsi. We need to calculate. The freezing point depression constant Kf is given this much. And you can see the freezing point of depression for the solution of molality is also directly given. How much depression is there? We need to calculate that. Means, you know, the formula delta TF is equal to Kf into N. And we need to calculate this delta TF. Okay. So it's very easy. You can see this is delta TF has a value that is 5.12 into molality has a value 0.078, and if you are going to solve it, you will be getting 0.40 Kelvin. Since this is temperature, so the value will be in Kelvin. Is that clear? Umam and Austin.
Yes,
Austin. Okay. Can I change the slide? Moving to the next colligative properties and the last colligative properties, that is your osmotic pressure. So before starting this osmotic pressure, I would like to introduce a new term that is your, this is your osmotic pressure, and the term that I am going to introduce, you are already aware of this, that is called osmosis. Are you aware of this osmosis? Basically, it is movement of solvent particle. Always remember that this solvent is smaller than solute in size. Okay, so I'm gonna explain this. As you can see, there is a container in which there is a boundary in between this, and this boundary is your semi-permeable membrane, SPM. We call it semi-permeable membrane. What is this semi-permeable membrane? Actually, this semi-permeable membrane has very small pores through which only solvent can pass. Only solvent can pass, because solvent are very small in size as compared to solute. So through this semi-permeable membrane, only solvent will pass. So if there is concentration C1 and if there is concentration C2, and if C1 is greater than C2, if I will tell you that this there is two container we have. In container A, there is concentrated acid, and in container B, that is dilute acid. So you know that in concentrated acid, the solute particles, the acid particles are more, and in dilute acid, you have more solvent particles. So if the concentration on the left hand side is greater, that concentration, that means solute particles is greater, that means the solvent particle will be lower. And here it is solute particle will be lesser and solvent particle will be greater. So the movement will start from right to left. Always remember that if you have two tank of water, one is fully filled and one is just this much filled. And if you are going to connect this with a pipe, what will happen? The flow of water start from right to left, basically high potential to low potential. What I want to tell you is that if concentration is more, that means solute particles is more. If solute particles is more, that means solvent particle is lower here. Solvent particle is smaller, very low. And if here the concentration is low, that means solute particle is low and solvent particle is more. And as you can see, the high potential will be here and the low potential will be here. And that's why the particles start moving, solvent start moving from right to left. So I'm gonna just define it. Is that clear, both of you, Austin and Humamuddin?
Yes.
Yes, sir.
Okay, just write the definition. We can define this in two terms. In terms of concentration, whenever I will say, or if you are reading anywhere that the concentration is high, that means solute is high, solvent is low. So the movement of the movement of solvent molecules from their higher concentration to lower concentration to lower concentration of solvent. So it's very easy. This is in terms of this is in terms of what? Solvent. Now the next we can define the movement of solvent molecules from lower concentration of solution lower concentration of solution to higher concentration of solution to higher concentration of solution through SPM you can write to SPM. So the next definition, the other definition you can see. I said that the movement of solvent molecules from lower concentration of solution. From lower concentration of solution. Concentration of solution, that means we are talking about solute. If solute will be lower, that means solvent is higher. To higher concentration of solution, that means concentration of solution means we are talking about solute. If higher concentration of solute is there, that means lower concentration of solvent is there. So the both are same name. Please do write. Let me know when you are done with this. Austin and Mohammed, are you done with this?
Yes.
sir.
Austin.
Yes.
Okay. Now, this was about osmosis. Now we are going to start this osmotic pressure. For osmotic pressure, I am going to draw a diagram. Please do this with me. See, this is your piston. Here, this side, you have piston, which you can adjust according to yourself, increase or decrease the pressure with the help of this piston. And here it is atmospheric pressure, 180. That is open, atmospheric pressure is there. Now, the next and important point is that there is your SPM. This is your SPM through which only solvent can pass. Now, on the left hand side, it's your solution, and on the right hand side, it's your pure solvent. Pure solvent. In solution, you know that solute and solvent both are there. Now, my question is that, what do you think? Where will be the movement from right to left or left to right, or there will be no movement? What do you think? Muhammadin, Austin.
Yes, sir.
The movement of solvent particle will be from right to left or left to right. Very good, Austin. From right to left. Why? As you can see, on the right hand side, it is pure solvent. Here, the substance that is present is your pure solvent, and here you can see it's your solution in which solute is also there. And I just defined that in osmosis, higher concentration of solvent, from higher concentration of solvent, that means the side on which the concentration of solvent is more will start flow from there to the side on which the concentration of solvent is lesser. Are you getting my point, Humamuddin?
Yes, sir.
So the movement will be from right to left. Is that clear?
Yes, yes.
Have you written it all? Austin and Humamuddin?
Yes.
Yes, sir.
Okay. Now, what is your osmotic pressure? Why we introduce osmotic pressure? So see, here is your piston. And since this is your pure solvent on which on the right hand side, the concentration of solvent is more. So it will start flowing from pure solvent side to solution side. Now, what you are going to do, you are just going to apply pressure here with the help of this piston. Basically, you need to apply that much pressure just to stop this osmosis process. Just see, if this will start from flowing from right to left, you can stop this uh, process. You can just stop this flowing of solvent from right to left by adjusting this piston. By applying pressure on piston, you can stop them. And that pressure that you are applying, that pressure is known as osmotic pressure. So I'm gonna define it. The net movement of solvent molecules from solvent side to solution side can be stopped by applying an extra pressure. By applying an extra pressure over solution side, which stops osmosis. And this extra pressure is called osmotic pressure, that is denoted by simple. So you have solvent side, you have solution side, flow of solvent side from solution side. This can be stopped by applying an extra pressure. That pressure is known as osmotic pressure. So it's very easy, right? Let me know when you are done with this. Are you done with this?
Yes.
Umam?
Yeah, yes, sir.
Okay. Now again, we are going to derive a formula in the same way, experimentally. We found that phi, that means osmotic pressure, directly proportional to molarity. This is your molarity. In some books, it has been denoted by C. C is also concentration or molarity. And phi is directly proportional to T as well. T is your temperature. Now you can combine these two equations and it will be directly proportional to MT. And to remove this proportionality sign, we are going to use a constant, that is our gas constant, ideal gas constant, RMT, or you can write phi is equal to MRT. The value of R, that depends upon in which unit you are taking. So one of the value I'm going to write 0.083. That is your liter bar per mole per calorie. And you already know what is molarity and all. Are you done with this?
Yes, sir.
Yes.
Okay. Now I'm gonna give you a question on this. Calculate osmotic pressure due to 5% weight by volume. Sugar solution at 15 degrees centigrade. Are you done with this? Okay, let me explain. See, we need to calculate osmotic pressure, temperature is your 15 degrees centigrade. So you can easily convert this into Kelvin, and that will be equal to 15 plus 273. That will be equal to 278 Kelvin. Now, see 5% weight by volume, that means 5 gram of solute, that is sugar, present in 100 ml of solution. 100, since volume is there, 100 ml of solution. That means volume of solution is 100 ml and mass of sugar, that is solute, is 5 gram. Sugar has a formula C12H22O11. Now we are going to apply the formula pi is equal to mRT. R we already know. M has a value number of moles of solute upon volume of solution in liter. And R has a value 0.083 you can take. And temperature has a value 278. Now you know that this number of moles has a formula. Again, given mass upon molar mass, given mass is 5. And if you are going to calculate the molar mass of sugar, that will be 342. The volume of solution is 100 ml and you have to convert this into liter. So we need to divide it by 1000. And again, you can see R will be equal to 0.083 and into 278. You can calculate this after, right? Austin and Humamuddin.
Yes.
Okay. So this is it for today. If you have any doubt, you can ask me. Humam.
Yeah, no, sir.
Okay. So I'll see you in the next class. Thank you.